It gives me great pleasure to congratulate Dr. Joseph Vacanti for being a Regenerative Medicine Foundation honoree. Dr. Vacanti is a Homeland Professor of Surgery at Harvard Medical School, and he served as the Chief of the Department of Pediatric Surgery and Surgeon-in-Chief of the Mass General Hospital for Children. As an academic surgeon, Dr. Vacanti has been active in clinical innovation as well as basic research. He instituted the nation's first liver transplantation program specifically for the pediatric population. Dr. Vacanti has been working on the field of regenerative medicine since the 1980s. Over the last 20 years, Dr. Vacanti has studied creating complete vascular networks as part of implantable tissue engineered devices, which then allows the fabrication of large, complex living structures. To further the field of tissue engineering, Dr. Vacanti was a founding co-president of the Tissue Engineering Society, now the Tissue Engineering Regenerative Medicine International Society. He also was founding senior editor of the journal Tissue Engineering. Dr. Vacanti has authored over 300 original reports, written over 70 book chapters, and he has 83 patents or patents pending in the US, Canada, Europe, and Japan. He has received multiple awards, including the Thomas Sheen Award, presented by the New Jersey chapter of the American College of Surgeons, the James Bartlett Brown Award from the Society of Plastic and Reconstructive Surgery, and the Clemson Award from the Society for Biomaterials. In addition, he was elected in 2001 to the Institute of Medicine. In 2007, the Board of Directors of City Trusts, acting for the City of Philadelphia, awarded Dr. Vacanti the John Scott Medal. In 2009, he became the recipient of the American Surgical Association's prestigious Flance Carl Award. Dr. Vacanti became a 2011 Thomas Reuters Citation Laureate in the field of physiology or medicine. In 2013, the American Academy of Pediatrics Section of Surgery named Dr. Vacanti the recipient of the William Latt Medal. In June of 2015, Dr. Vacanti received the Jacobson Innovation Award from the American College of Surgeons. In 2017, Dr. Vacanti received a Lifetime Achievement Award from the American chapter of the Tissue Engineering and Regenerative Medicine International Society. And in 2018, he was elected to become president of the American Pediatric Surgical Association. Aside from all the accolades he has received from his peers, the most impressive aspect of Dr. Vacanti is his personal touch and mentorship ability. I personally benefited from this. It gives me great pleasure to personally thank Jay as a dear colleague and a friend, and as a visionary leader who helped to guide the field to where it is today. And on behalf of the Regenerative Medicine Foundation Board, to congratulate you for being recognized as the 2021 Stem Cell and Regenerative Medicine Lifetime Achievement Honoree.
I would like to thank the Board of Directors of the Regenerative Medicine Foundation for the honor of being selected to receive the Stem Cell and Regenerative Medicine Action Lifetime Achievement Award. And I would like to thank all of you for the privilege of speaking to you today. As you all know, any success in regenerative medicine requires the close collaboration of many disciplines in science and medicine, and close partnerships in academia, industry, and government. This World Stem Cell Summit represents those communities in a very real and vibrant way. In my brief remarks today, I would like to focus on one of the holy grails of regenerative medicine, the manufacture of whole vital organs on demand to solve the terrible donor organ shortage in transplantation. I will put it into the context of my personal quest over the past 36 years and then suggest a future direction. Before I begin, I would first like to acknowledge three individuals who have been essential to my professional development and efforts in this arena. Dr. Judah Folkman of Harvard, my mentor and teacher over 35 years. Professor Robert Langer of MIT, my friend and collaborator of over 44 years, and my brother Charles over a 70-year period. At my core, I am a clinical surgeon. This is one of my patients with a fatal liver disease who could be saved only by liver transplantation. This is how I became acutely aware of the organ shortage in a very intimate way. In 1985, while working on ways to increase the number of donor livers for children by implanting pieces of larger organs which were trimmed to the proper size, we experimented with biodegradable polymers or plastics to seal the bleeding surface of the liver. As I studied the effects of healing under the microscope, it occurred to me that we might be able to use the polymers to deliver cells to patients in an organized way, a type of cell therapy. We had early success with this approach, but there was a huge problem. An adult human liver weighs over 3 pounds, and so to actually help a patient, many billions more of liver cells to make liver tissue would be necessary. There was a major design constraint to overcome, as you see depicted here. If these spheres represent spheres of cells, each cell needs oxygen to breathe and nutrients. Both are only delivered at the surface, and so as a mass of cells increases in size, the surface cannot keep up with the demand, since the mass of cells increases as the cube of the radius, but the surface only increases as the square of the radius. I struggled with this problem for months until the summer of 1986. How could we make the cells on the inside think that they were on the outside? And then, while sitting on a jetty on Cape Cod in the summer of 1986, pondering this dilemma, the answer was waving in front of me. All of nature in all multicellular organisms, both animal and plant, solves this problem using branching systems to nourish every living cell, no matter how large the structure. Nature breaks the surface into massive surface areas for exchange of nutrients and oxygen. In us, the vascular or blood vessel system acts in this way. Here is a vascular cast of a lung, showing the exquisite branching down to the smallest capillary channels, each of which is 1/10 the diameter of a human hair. Using these branching patterns as templates for the scaffold design, we rapidly produced living tissues of many different types. And of course, in 1997, a mouse with a living human ear on its back went viral from a BBC television show. The controversy surrounding this image propelled the new field of tissue engineering into the public consciousness. New work in stem cell biology led to the creation of the term regenerative medicine, and stem cells became an important foundation for tissue engineering approaches. We continued our work in trying to increase mass to create vital organs, and in 1998 began to build vascular channels within our tissue engineered devices using computational fluid dynamics to build models which duplicated the flow characteristics of the normal blood circulation. Here you can see the blood vessels in a normal human liver. Here you see a 3D printed pattern of blood vessels into and out of a device that also contains the liver and bile duct compartments. Here is a recent design showing the extreme precision we can now achieve in vascular channels using 3D printing technologies. I hope that this very quick summary of my involvement in this emerging field gives you a sense of its promise and potential impact in human health. We are still in the early phases of the science and engineering of regenerative medicine. I can compare it to the early days of rocket development. Here is Dr. Robert Goddard in 1926. This first liquid-propelled rocket flew for 2.5 seconds to a height of 41 feet and traveled 184 feet. Compare that to the Saturn V rocket, which flew men to the moon 43 years later. I will leave you with this image. It represents the talent and commitment of a diverse group of professionals in many fields, tackling the problems in our field at least as complex as rocket science. Thank you again for the award and the privilege of speaking to you today.